Let's do some Gaussian surfaces, specifically with cylindrical. Cylindrical, linear. We'll do electric field due to a line charge using a cylindrical Gaussian surface. There we go. All right. This is a continuation from my first Gaussian video. We're going to go do a couple of free response type questions that you might find on something like an AP test. So, starting with, so we have a picture, okay, little jaggedy edges, got it. A very long, i.e. practically infinite, long cylinder, non-conducting, radius r, check, has a positive meaning, I'm going to start circling things, means that all the charges, arrows are pointing out. Has a uniform volume density of rho. Okay, that makes sense. Pretty standard. A section of the cylinder far from its ends. There, okay. That way we can assume that it's no end effects. It's all just uniform and infinite. Though if it is infinite, it would also be far from the ends, pretty much by definition. Okay, as shown in the diagram above. Okay, and I think that's what the jaggedy edge means. Jaggedy edge means it goes on forever, and they're just not going to draw forever because they have limited paper that they can use. Let R represent the radial distance from the axis of the cylinder. Okay, so we'll have, I'm going to draw it like this. R. Arg. Express all answers in terms of R, and rho. That's interesting because they're all basically R. Maybe a pirate wrote this problem. In fundamental constants as appropriate. Using Gauss's law, okay, derive an expression for the magnitude of the electric field at a radius r less than r. Draw an appropriate surface, Gaussian surface, on the diagram. Next we'll do derive an expression for the magnitude r greater than r, which makes sense. On the axis below, I always wonder if it's axis or axes. I don't know. I should look that up. I wonder if there is a difference. Interesting. Okay. As a math guy, I should know these things. Anyway, moving on. Don't get distracted. Focus. Sketch the graph of an electric field E as a function of radial distance r, for r equals r0 to 2r. Okay. Explicitly label any asymptotes, intercepts, maxima, minima with numerical values or algebraic expressions as deemed appropriate. And yep, this is probably good enough for now. Okay. Gauss's law for r less than r. So start by writing out Gauss's law. Actually, I'll write it up here so I have it, the diagram as a reference. So we have Gauss's law is, what is it? Q enclosed over epsilon naught equals, do I got this? Double integral E dot dA. Yes. Huzzah. Okay. And we're supposed to find, use Gauss's law, derive an expression for the magnitude of the electric field. Click, clack. All right. So I'm going to start by drawing that. Okay, and this is for r less than big R. So we know that the electric field, due to its symmetry, is going to go radially outward. I don't really have a good way of justifying this other than you look at it and it's kind of obvious. It's symmetrical in every other way, so there's really nothing else it can do. But if you want, I guess, a little bit more of a warm fuzzy, if you look at it from along the axis, you'll get some, so I have a charge that goes in all directions. I know I'm only doing a few here. And then you'll have another charge over here that does all directions. And looking at just the top portion, this vector would cancel with that vector, that cancel with that vector, and what you're left with is only the radial components going outwards from the axis. The radial components that are perpendicular to the axis of the cylinder. And so that's all that we're going to be looking at. I think Most people probably say, well, you determine it by inspection, which is a fancy way of saying it's obvious, or you should just know this, or guess and check. So let's see here. We also then need to find Q enclosed. And they gave us rho, where they said rho exists, it's uniform, and it's greater than 0. So Q enclosed, you can, the Gaussian surface we're going to use will be a cylinder, because that way, what we want is we want the magnitude and the angle between the electric field, which is radially outward, and the area, which is also radially outward because it's a cylinder. We want those two to be, we want the angle between the two to be same for every point, for every electric field and area. And we want at every point, we want the angle between the area and electric field to be the same. And we want the magnitude for every given area on the Gaussian surface to also be the same. So we're looking for magnitude and angle. And what that means is, so we can kind of sort of rewrite this as E times, now let's do it, cosine theta, which is the angle between the area and the electric field, dA. We want this to be a constant. And if it's a constant, it means we can pull it out of the integral. Integral. We can pull it out to the side, and that way it'll be much easier to solve for the area. Okay. Focus. Q enclosed. So we're given rho. When I do this kind of in a long form, I overanalyze it. So rho basically means for a small given amount of Q, for a given amount of volume, you get a constant rho. And then I rearrange this as rho delta V equals delta Q. And then to find Q enclosed, I then integrate rho delta dV, where this is volume, integral dQ. I know I'm not very consistent, that's okay. And that will give us Q enclosed, because that's the entire Q enclosed by our volume. And then our Gaussian sphere for this, since we're looking for R, small r less than big R, we're going to do a Gaussian surface like this. Now draw a squiggly line, and probably do it the other side too. Squiggly line, and like this. Where right there is R. Okay. So what we need to find then, so rho is going to be the same, and then delta V. So this is going to be the volume of our Gaussian sphere within R. And the volume will be the cylinder. So we got pi r squared, which is the area of one side, times, I'm going to say length, where length is the L of our Gaussian shape. So this is L, which we assume will cancel out. Maybe. I hope so. Maybe. Times rho equals Q enclosed. Okay? That's our Q enclosed. And then we need to find the other side. So since the electric field and area, so the electric field and the angle between the electric field and the area will be constant all over our Gaussian sphere. Gaussian shape, which is a cylinder. So we have double integral, ignore that, E dot dA equals electric field magnitude dA. I left the cosine of theta out because the cosine of theta is cosine of 0, which is 1, and therefore can be ignored because it's the identity element for multiplication. So what we need to find here is the area. So the area of our Gaussian cylinder will be, okay, so we're going to have two areas. We're going to have the area at the end caps of our cylinder. We can just make it an infinite cylinder. Okay, we're going to have our area at the end caps, and we have the area at the top. The area at our end caps, it's actually going to have a different electric field and different angle than the outside. So it was probably premature of me to just yank the E out. But I'm going to mitigate my failure by saying that at the end caps here, the cosine of theta, in this case, equals cosine of 90, or pi over 2, which equals 0. And therefore, that can be ignored. So I'm only going to find the area of the top part of the cylinder that's shrouding, enclosing. I got thesaurus for the holidays. 2 pi, so the area would be electric field times 2 pi r, which is the circumference of a circle, times whatever the length is of our cylinder. So we can then have, putting everything together, so this is, make sure we got most everything. So Q enclosed over epsilon naught equals, okay, this is our entire formula. This is the Q enclosed part. So we have Q enclosed, pi r squared times L times rho over epsilon naught equals E times 2 pi r times L. Okay, that's what we'd like. Switch colors to add emphasis. Not enough contrast between red and orange. Blue. So then electric field equals, we only want the magnitude. Cancel, 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 cancel. Equals rho times Z over epsilon naught. Okay, I would believe this. So rho, I'm going to do rho times r, little r over epsilon naught. Rho r epsilon naught equals electric field. Ooh, and there's a 2. Almost forgot the 2. Thanks, guys. Letting me down there. Put a little 2 over here as well. So rho over 2 epsilon naught. Rho r over 2 epsilon naught. Memorize that, write it down. Electric field equals rho times r over 2 epsilon naught. There we go. I'm good with that. Yep. Very satisfied. Alright, now use Gauss's law to derive an expression for the magnitude of the electric field where r is greater than r. Okay, so the only part that changes here now, so the volume, it used to be where the volume enclosed was this, we could relate the volume enclosed to the surface area of our Gaussian cylinder. Now our Gaussian cylinder is actually bigger than the cylinder that we're enclosing. So these two r's, here and here, will no longer be the same. So I'm going to take the same equation we just had written up and rewrite it in terms of, so we're going to have rho times, okay, now this one is the volume, and the volume enclosed will be pi r squared times L times rho over epsilon naught, because this is the Q enclosed. So what we're talking about is, at this point, use Gauss's law. Do we have to draw? Okay, so now we have another Gaussian cylinder with r greater than r. And it goes this way as well. Okay, and then we go back to r times little r over 2, okay, this equation up here, equals E times 2 pi r times L. Yep. The pi's, though, will still cancel. Always sad to lose pi. Cancel, cancel. Lengths will cancel, which is good because we don't actually know really what the length is. Electric field equals r squared times rho over 2r. And if you look, the units are still the same though, because before we had a r on top, but now we have an r squared on top and r on bottom. Both are measured in meters or distance or whatever, whatnots. And even though we have an r squared on bottom, it's now kind of sort of canceled out by a different r, but of same units on the bottom. So our units will still work out. So this is for r greater than r. Whoop, whoop. And I could write it over here, or I could just do a copy paste. Haha. No, too cluttered. So, right there goes to there. Okay, on the axis below, sketch the graph of the electric field E as a function of R. Okay? From 0 to 2R, explicitly label thingamajig. Okay. So, if this was a question you got on the AP test, you'd have about 15 minutes to do the whole thing, which would mean you probably have to be going quicker than I am going now. I try and explain things a little bit more in detail than you would if someone just rushing through the exam. But yeah, you'd have to move quicker. Okay, so let's see here. So the first equation we're going to have is this one. So from 0, we're probably going to start with r equals 0, and then it's going to go up linearly, because everything here is a constant except for r. It's going to go up linearly until we get to r. And then once we get to r, it'll go down, what is that called? The 1 over r thing? It'll go down as of 1 over r. So this is linear, and this is proportional to 1 over r. So I probably should have used more of the graphs. Probably should have done something like, whoop, shoomp. That's too much. That's a little much, but same idea. I can do better. I can do better. Whoop. Then do an asymptote, because they'll never actually get to 0. Yep, I am good with that. Then derive an expression for the magnitude of the potential. We haven't talked about voltage yet, so we're going to pass on that one for now. Come back to it in a later date. The non-conducting cylinder is replaced with a conducting cylinder of the same shape and same linear charge density. So now they're saying they don't give us rho, they're giving us lambda, which is for a small change in charge, a small change in distance, length, on the axis below. And the reason they do that is because for a conducting cylinder, we have all the charge is on the surface. And so they could give us a sigma, surface charge density, which would be a small change in area, small charge for a small change in area. But they can't give us a rho, because rho would be 0, because the volume, most part, the skin effect, the volumetric density would be practically 0 throughout the entire cylinder with all the charge on the surface. On the axis below, sketch the electric field as a function of r, for r equals r, explicitly label any intercepts and so blah 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 blah. Alright, so I'm going to quickly write out Gauss's law. So Gauss's law is Q enclosed over epsilon naught equals double integral surface E dot dA. And so when you look at the cylinder, like so, all the charges are at the surface edges. I know we can draw the surfaces on the here too, but my artistic talents are limited here. So bear with me. So the idea here that I want to go for is for R less than big R, Q enclosed is 0 because there's no electric field, there's no enclosed charges within on the inside of the conducting cylinder. They're all on the surface. But once we get to the outside, we get all those charges all at once. And so what's going to happen then is we'll get the full power, I guess, of the electric field all at once. So it's going to be the same as above, but it's only going to be same as above for, and then asymptote at 0. It's terrible, but you get the idea. And then you'll have the step jump along right there. So that's Yep. That's the idea behind that one. So what they're asking you is for you to know so there'll be a step jump because within the conductor there will be no charges, no Q enclosed. Okay, so that one probably took me about 25 minutes to go through that. I skipped one part of it, so you'll have to move, I don't know, maybe 30% faster than I did. Less dialogue would probably help. And it's probably frowned upon if when you take the AP test you keep talking to yourself, narrating what you're doing. Gosh, that would be humorous, though you'd get kicked out quite quickly. Alright, so now let's move on to another one. Okay, so for this one, we've now moved on to a slab. A square, rectangle, prism. A very large, non-conducting slab. It is a slab. 1 out of 3 isn't bad. Slab with a uniform positive volume density of rho naught. Okay? And it's positive, which means that the arrows go out, which is useful to know. It's fixed with the origin, the x, y, z. Okay? As center shown above, thickness of the slab is d. Okay? And the length is L. Okay? And the width is W, where L is significantly larger than D, and W is significantly also larger than D. So what they're saying is we can treat this as an infinite plane. Since all the thickness is negligible, thickness as in D is negligible compared to the length and width. So the large faces of the slab are parallel to the XY plane. That is also convenient. Consider a Gaussian cylinder, okay, with a cross-sectional area A and height h that is positioned with its axis. I guess axis is singular and axis with an E is plural. I'm good with that. Along with the z-axis as shown in the figure below. Okay? Figure below is seen. And draw a single vector on the dots below. So it looks like the Gaussian cylinder is within the slab, inside the slab. So similar to the previous problem where we had the cylinder within the cylinder, this is a cylinder within the slab. Draw a single vector on each of the dots below representing the direction of the electric field at the points. If the electric field at either point is 0, write E equals 0. Okay? So we're talking about R and S here. So at this point, the electric field is going to be outward on both sides. This is due to the symmetry. So again, you're just going to kind of have to look at it and be like, okay, this makes sense. So if you look at R, you can see that there's like a top and bottom, above and below the cylinder, which are symmetrical. And those would be like two parallel planes. Parallel planes create uniform charge, uniform electric fields. And so the top and bottoms will cancel each other out. And so then we're left with basically a plane in the middle, which will create a uniform charge away from the middle. So I'm going to try to reassure you that R is up, S is down. I know that was not a lot of... I'm glad they don't ask you to justify this on the problem, because there would be a lot of hand waving involved, which looks awkward when you're taking a written test. Use Gauss's law to derive expressions for the following. Okay. Express your answers in terms of rho, A, D, H, and Z. God, that's a lot of things. Ooh, and then every physical constant as deemed appropriate. Derive an expression for the flux, okay, through the Gaussian surface as shown. Okay, so one thing that I've glossed over when talking about the Gauss's law was flux. So the way Gauss's law is actually set up is Q enclosed over epsilon naught equals electric flux, and electric flux equals double integral surface E dot dA vectors. And so what I did was I was like, okay, we really don't need to worry about that flux in the middle there, since you just use it, basically set one side equal to the other. Well, for those of you who don't know what flux is the, if you're given an area, flux is the amount of, let's see, I assume it's the vectors within that area and then their dot product that goes through it. So it's the amount of flow through a surface. The which is pretty much the same as E dot dA. The common analogy that's used to explain this is you're off in the world and nope, you don't have red clouds. You have a stormy cloud. I know it should be more of a gray. It's okay. You'll get the idea. And you forgot your umbrella, but luckily you have a hula hoop. And so you take the hula hoop, and when you take the hula hoop, if you hold it flat to the ground, then you'll get maximum rain flowing through the hula hoop. But if you hold your hula hoop up and down like this, then you'll get almost no rain going through your hula hoop. And so the rain here represents the vectors falling downward, and the flux then is the amount of rain falling down multiplied by the angle of the surface that you have. So to get maximum flux, you'd want your hula hoop to be parallel to the ground, and therefore the rain would fall straight down. Actually, it'd probably be minimum because you get a negative value. We're not worried about, we're looking at magnitudes right now. But when you held your hula hoop sideways, up and down, all the rain would come down on the sides of it and be not fluxed. And so that's the idea of flux. It's the amount of flow through a surface area. So what we're looking for here is E dot dA. Or we could do like Q enclosed. Interesting. Either one we could find and say, oh, that's flux. Okay, derive an expression for flux through the Gaussian surface. Okay, so we're just going to do Q enclosed over epsilon naught, because either one of these equations will do it. So for Q enclosed, I know that is quite tangential. So we're going to go for this one right here, though we could use the other one. We'd have trouble using the other one because we don't know what the electric field is. So we have rho naught, which equals a small amount of charge for a small given amount of volume. Delta V times rho naught equals delta Q. Take the integral of both sides, rho naught, which is a constant and can be pulled out, equals delta Q, which will be Q enclosed. This goes over there. And integral delta V, rho naught. This volume will just be the volume of the cylinder, which, looking up here, is about that much. So we're going to have, it goes up h over 2, down h over 2. And we, they give us A. What was A? I assume A is the area. For terms, did they tell us what A was? Man, they give us so much information. Cross-sectional area A and h of height. Okay. So, the volume will be A times h. And then we'll throw in rho naught. So, the electric flux equals area that they give us, cross-sectional area, times the height, times rho naught over epsilon naught. Flux equals A H over epsilon naught times rho naught. Okay. Yep, and that's all we have to do for part A. Derive an expression for the magnitude of the electric field as a function of Z for any position inside the slab and show that it is equal to. Okay? Okay, so for this point, we're going to say that H equals Z. Probably. Yes. So I'm going to quickly erase this, give myself some space. And so I'm basically going to ignore the first part and say derive an expression for the magnitude of the electric field as a function of Z for any position inside the slab. And then they give us the answer just so we don't get too far astray. Okay, so we'll say that, I think we did something similar on the previous question, so this should make sense. So we got Q enclosed over epsilon naught equals double integral E dot dA, clickety clack, okay. Q enclosed, we already decided would be A times Z, because looks like we switched A, H, and Z here, rho naught over epsilon naught equals electric field. So the electric field will be constant outwards at all these points. And we can ignore the sides of the cylinder because the angle between the electric field and the area will be pi over 2 or 90. And therefore cosine of 90 is 0. But we have to account for the top and bottom, and that will be pi r squared, pi, that'll just be the area, because I think they give us A. Is it independent of area? Interesting. Okay, so now we just need to find the electric field. And we get E equals rho times Z over 2 epsilon naught. Is that what they wanted? No, they have 1 epsilon naught. Okay. So here's the thing. So Z is just half of the length. So so they're going from positive Z to negative Z. You tricky. Okay. So we're going to have to double Z here. So the Q enclosed will be 2Z, which then gives us electric field equals, does that give us the right direction we want? Yep. So then the 2's will cancel. Then we get rho times Z. It's supposed to be 2Z. So we have the electric field is rho naught times Z over epsilon naught, which is what we wanted. And the trick there was that from the top to the bottom, it's going to be 2Z's, two Z's, as opposed to just the 1H. Okay, proven. All right, so now we got this slab. This one seems to be a lot of reading for very little actual work. Charged slab is now placed between two large metal plates separated by a distance of 1 centimeter? 1 centimeter, which is approximately the thickness of the slab. But the slab does not contact either metal plate. Okay? The metal plates are charged, resulting in the surface charge densities of 2 times 10 to the negative 6, so 2 microcoulombs per meter squared, okay, as shown in the figure above. Assume the charge distribution inside the slab remains unchanged, therefore uniform and positive, by the presence of the charged plates, and that the slab's volume charge density is 1 times 10 to the negative third coulombs per cubic meter. Oh, so they actually give us rho, okay? The magnitude of the electric field inside the slab is 0 on the z-axis. Which of the following correctly indicates the value for Z naught? The magnitude of the electric field inside the slab is 0 on the z-axis. Okay, I assume the z-axis is x, y, okay. I assume that's at z equals 0. Which of the following indicates... Oh, okay. Okay. So basically we want to find out if the electric field from the slab is stronger than the electric field from the plates. Interesting. Okay, so electric field plates. So we know the electric field is, for a infinite plane, is sigma over 2 epsilon naught, but we have 2 of them, and so will equal, I'm going to draw this out real quick. So the electric field lines from this plate go like this. The electric field lines for this plate goes like this. Nope, goes in. And so between the two plates, they're going to be going upward. The electric field is going to be going upward. So we have, since we have 2 of them, we'll have 2 epsilon. I'll draw an arrow, so it's kind of not really equal, but related. 2 plates, and that's going to be 2 times 10 to the negative 6 coulombs per meter squared over epsilon naught. Okay? And then electric field from the slab, we probably already have something that tells us what that equation is. Was that this one? Yep. Wish I'd written it more clearly now that I thought I'd actually have to use it. Rho times Z over epsilon naught. And they give us rho, and we know that Z is going to be... We don't know what Z is going to be, but we'll find it out. 1 times 10 to the negative third. So 1 times 10 to the negative third over epsilon naught times z. And then if we set these equal to each other, so the electric field from the slab is going this direction and it's going that direction. Oh, we don't have to calculate z until the second part. Oh well. Alright, so it's going up and going down, and then the electric field from the plates is going this way. So the only place where they would be able to cancel each other out at all is in this area. So for z less than 0. So we're going to set that these are equal to each other. Is that fair? I'll set them equal to each other. I might get a positive number, but I'm going to know that it should actually be negative. So we have 10 to the negative third. I dropped the 1 because it's just a 1 over epsilon naught equals 2 times 10 to the negative 6 over epsilon naught. Change colors so we can accentuate the canceling. Cancel, 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 cancel. Therefore, z equals 2 times 10 to the negative third meters. And we know that'll be negative. Do we know how big this z is? Or how big the slab is? That's 2 millimeters. Okay. Which is less than 1 times 10 to the negative second meters. Which makes sense, because if we got that the z point had to be out here somewhere, then we'd know we were wrong. So I'm going to say that z is 2 times to the negative third meters. Check. Calculate the magnitude of the electric potential difference. We're going to skip this one because we haven't covered potential yet. Okay, and that gives a good overview of how Gauss's law can be applied. Yeah, it's not too bad. Not too bad. I would recommend trying to actually learn Gauss's law. I know you can kind of wing your way through it and just kind of fudge things. I would not recommend that for this. Gauss's law is easy enough to learn that it probably actually is worth your time to just get an idea of how it works. Q enclosed over epsilon naught equals surface integral of E dot dA. You're choosing your Gaussian shape so that the electric field and dot dA, you're going to want the angle almost always, not always, but almost always to be 0 or pi over 2, either parallel or perpendicular. And then the only way you can pull the electric field out of the integral is if at all points on the surface that you've created, your Gaussian surface, the magnitude and angle between the electric field and the area are the same. And if that is constant, the magnitude and angle, then you can pull it out. And then that makes life so much easier. And then the way that I find Q enclosed, which you're almost always going to be of this method, is you might be given rho or sigma or a linear charge density, lambda, and I just rewrite that as a small amount of Q for a small amount of volume. If you have sigma, it'll be a surface charge density, which of course you'd use area. Get lambda, then you would use a dl, and then you're going to have a rho delta Q, integral of both sides. I know my notation is terrible, but I think this helps preserve a lot of the conceptually what's going on. Okay, sounds good, and I will see you gentlemen and ladies next time.